colleagues here at the University of Iowa, but don't tell them I said so. Mike Shai, who I've known for a long time, and was one of the reasons why I came to the University of Iowa, because of his excellent track record and good, clear scientific thinking and clinical research. And so Mike Shai can talk to us about his role and the story of track record.
Thanks, Lori. And I didn't know I was one of your favorite people, so I feel much better now. And what I'm going to talk about is our work through the years in inherited neuropathies, trying to bring an understanding of these diseases to the point where we can do clinical trials. And as you'll see going forward, I am definitely not an expert and was not an expert at the beginning, but I do have a fair amount of experience. So hopefully some of these lessons will come through, and feel free to interrupt me with questions if I'm too far out of left field. So the disorders that I'm interested in are genetic diseases of the peripheral nervous system that are referred to generally as Charcot-Marie-Tooth disease. And when I started my career, nobody knew anything about the causes of these diseases other than what's sort of summarized in the next slide. And this shows basically that these genetic disorders, you can separate them into two large groups. These are diseases of the peripheral nervous system, and one group is caused by mutations in genes that damage myelin, and those are called CMT type 1 or HMSN type 1. And then there's a second group of these diseases, which the genes damage the axons but not the myelin, and these are called CMT type 2. And the first genetic cause of disease was identified after I finished my training, probably at a stage similar to many of you in the group here. And this was in 1991, the genetic cause of what's called CMT1A was discovered. And things have been progressing exponentially, particularly with next generation sequencing. So currently there are there are over 90 known genes that can cause various forms of CMT, and these genes are scattered throughout the chromosomes. So one of the reasons that people with careers like me, and perhaps some of you really like to get involved with genetic diseases, although they're rare, is because they give you a window into actually understanding the biology of neurological disease. In this case, for type 1, you get a window into the molecules and the cellular pathways that can cause demyelination. And in the type 2s, you get a window into genes that can cause axonal degeneration. And since you know the cause, unlike some other neurological diseases, you can try to really develop rational therapies. And then perhaps it's your hope that the rational therapies for the genetic diseases can help you with acquired diseases that may also cause demyelination or axonal disease. So this is a disease, of course, about working to take scientific knowledge to develop treatments and therapies and clinical trials. And because of the way we've approached this historically, these have largely been investigator-driven therapeutic approaches. And so for somebody like me, once you begin to learn a few lessons about the basic biology, the challenge then is to learn how to take your lessons to clinical trials, learn about clinical trials, get pharmaceutical partners interested in it, and also, because patient foundations are very active, to work with patient foundations. And I'm going to try to do the rest of the talk sort of around these first thing I'm going to do is I'm going to show you two examples of inherited neuropathies just so you can see that although there are 90 genes, and even though people tend to think of CMT as clinically sort of homogeneous, actually the rate of progression is different for different types of CMT, and this is something that has to be factored into clinical trial design. So I'm going to first show you CMT1A, which is the most common form of CMT, and this is caused by a duplication on chromosome 17 of a peripheral nerve myelin protein, named because it's a peripheral myelin protein, so PMP, and in its size, PMP22. And it was first discovered in 1991. People are just now learning about what it does in the cells, but there's not a mutation within the gene on these patients. They get a duplication of the entire gene as part of an overall duplication of the chromosome. And it causes a very characteristic phenotype, which we tend to call a classical CMP phenotype. And I'll just show you a couple examples. So this is a little girl. I'm a scientist, so I know that. And you can see that she's running up and down the hall. She's going as fast as she can. And she's not going to be able to walk on her heels. She's not going to be able to tandem walk. And if I showed you her deep tendon reflexes, they would be absent. And if I did her nerve conduction velocities, they would be slowed at about 20 meters per second instead of 40 to 50 meters per second. And if people have seen this slide before, they know that I always show it because this was an expensive film to get. We had to part with that teddy bear to get the film here. And you see that she just can't tandem walk. And CMT1A is a very slowly progressive disorder, so most patients never need wheelchairs their entire life, and they may need more ambulation aids as they get a little older. And I'll show you an example here of an adult with the same disease. And you'll see that he looks sort of similar to the girl I just showed you, and there is some variability in patients, but nevertheless, this is a fairly typical presentation that affects most people with CMT1A. And so when we're talking about clinical trials and clinical trial design, we have to do something that takes into account of the slow progression. Okay. Now I'm going to show you so CMT1A is the most common demyelinating form of inherited neuropathies. It affects about 1 in 5,000 people, and in fact, it affects about half the people who have CMT. On the axonal side, the most common form is called CMT2A, and the biology here is a little different. There are assorted mutations within a gene called mitofusin 2. Mitofusin 2 is encoded in the nucleus, but it goes to mitochondria, and it enables mitochondria to fuse together, which they need to do to get uploaded onto axons and to be transported up and down nerves. PMP22 is just really expressed in Schwann cells, but MFN2 is expressed ubiquitously, but in most patients it just affects peripheral nerves. And here the progression is different, which I'll show you in the next 3 slides. So this is a little guy who we first saw in Detroit, and I think you can appreciate that he's more severely affected than the last little girl I showed you, and he's got some proximal weakness also, which gives him a little bit of problems lifting his knees. But he's ambulating, and this is him at 7, and those are scores that we use and we'll come back to later. Okay. This is him at age 8. I'll show you one more. This is him at age 10. And this is here at Iowa. You see, I'm not doing any of the work. I let the father do it. But I think you can see he's progressing at a rate that is different than patients with CMT1A. And this is fairly typical for most of the patients who have CMT2A. So when we're talking about trying to do clinical trials, we have to be able to deal with the fact that certain genetic types of CMT progress differently than others. And for CMT1A, we can get lots of patients, but for CMT2A, it's harder to get patients, and we have much smaller numbers that we have to deal with in clinical trial designs. So this was sort of the situation we were in like around 2005, that we were understanding the biology of these diseases. We were starting to get cellular models, animal models were being developed, and we wanted to try to develop treatments. But we had this one minor problem, which was that nobody had a clue about rates of progression of any of these forms of CMT. And nobody had a clue about how to try to take something to industry, for example, to get them interested in doing clinical trials. And we also learned, this is a slide from the NIH you probably have seen throughout the week here, but this is the valley of death in biomedical research. And are people familiar with this content, with this statement? Okay. Well, let me just ask sort of a general question. Of all the candidate medications that come out of like cellular models or animal models, do you think it's a very high percentage that make it to use in patients and have successful treatments for these diseases? Like 95% or 90%? Or Robin or Will or Rory can probably give the exact number, but it's way down, probably well less than 1%. So you can tell me if I'm off there. So we had to deal with that. And also, we were beginning to reach out, as we were doing a little bit of the cell biology, to industry to figure out, say, hey, we've got these great genetic diseases. This isn't like MS, or it's not like Alzheimer's disease or Parkinson's disease at the time. We know the cause. So these are great diseases to get rational treatments for. So we want to partner with you. And this is basically the bottom line from industry, that they say, that's fine, but what's the assay you want to use? And we don't have the time or the resources to develop this for you. And by the way, what's the natural history? How are we going to be able to tell if a medication is effective? So I think that these are sort of the questions that when you partner with industry, particularly if you're coming from a situation where you're talking about investigator-driven treatments, that you really have to have ready to partner with industry if you want to get their buy-in. And this is sort of a main theme of the rest of the talk, and I'm going to sort of fill this out with some examples. So we started to put together a plan, and this is a slide that Lori gave me. And you can guess what the end reality was, and the clue is it wasn't the top line with the bicycle. So, and I'm going to just again emphasize this point because I wasn't an expert. I'm still not an expert, but you do learn from this. And what I really have learned is that you need to have a strong scientific rationale, and it's important to have even molecular targets there, because if you don't have those, you're not going to get buy-in from the industry. You need to be able to measure progression in multiple ways pathways, and I'm sure you've heard about that throughout this week, but you have to have strong outcome measures, strong clinical trial design, and then you need the infrastructure to run the trials. So if you want to have success in areas like I'm involved with, this is what you need. And then I'm talking about cellular cell biology as if I'm, an expert, and I know some stuff, but not that much. And I also had started working with a patient foundation in the early, around 2000, which was called the Charcot-Marie Tooth Association. And that's led to a lot of experience with patient foundations. I'm going to talk a little bit about that on the next slides here. And I have to build this up a little bit. So the CMTA started as basically a coffee club in Philadelphia. They would occasionally fund a fellow to do research in CMT. And they wanted somebody like me on their board to help be able to develop treatments for CMT. And I don't know how many of you have worked with patient foundations, but they mean well. They have a lot of successful people on them, but they don't know the science or the disease. And to have the CMTA really be effective, we had to really bring in expertise into the patient foundation to really be able to try to move things forward rationally. So here, I'll show you some of the people. So unfortunately, John Griffin has passed away, but he was a giant in our field and tried to understand the scientific basis of peripheral nerve disease. Laura Feltry went across the top, Steve Scher, Larry Rabbits on the left, and then basic biologist Chris Jessen, Rona Mirsky, and people who were really experts in trying to understand the disease to really get things going to understand the scientific basis for these disorders. And I'm just going to show you two examples, and these started in about 2005, and I'll just show you an early part of how this worked. And again, the purpose of these next sections is just to show you that you really, we felt it was really necessary to get solid science into what we were trying to develop therapeutically. So CMT1A, that first little girl that I showed you, that's caused by too much of a gene being made, too much PNP22. So there's overexpression of the gene. So the idea was how to develop a way to reduce the expression. And one way, and this is when I first started to get to know Robin actually, was to try to develop an assay by which we could screen for compounds that were already out there, either in the NIH libraries or in pharmaceutical libraries, that could measure PNP22 expression so we could see if we could turn it down. And we chose to develop an assay in cells because that allowed us to develop what's called a high throughput screen, where we could really screen PNP22 expression in thousands and thousands of compounds. But then we had to learn a way to be able to measure PNP22 levels that didn't require somebody having to go do an ELISA or immunohistochemistry, something like that, to look at the levels. And here, again, because of the way the CMTA was set up, we were able to bring a person like John Severin in. So John is a molecular biologist at the Weizmann Institute in Wisconsin, and I'm going to go through these next slides quickly, but John was an expert in how PNP22 is regulated, and he demonstrated, we knew that there was 2 promoter sites, but John found in an intronic region, next slide, sorry, an area where there were sites for 2 transcription factors, what's called CROX20, and one is, one called EGR2, and one is called SOX10. And these sites are important for not only regulating PNP22, but other myelin genes. So John built a reporter construct using this area here, instead of having the construct make KMP22 itself, it used a dual luciferase approach. And then we went to the intramural program with the NIH, which you just heard a little bit about. And we partnered with Jim Inglis there, and who had a robotic system in place to look at these cells. And this is just, I think, just showing you the robots in action. But by taking John's cells and using Jim's system, we were able to set up an assay where we could look at basically hundreds of thousands of compounds. And this I'm going to just leave up here as I'm talking. And this enabled us again to screen these assays, screen these cell lines with libraries, initially at the NIH, but then we were able to get industry to buy in, so Sanofi Genzyme bought in, and this is our first way to get industry involved in what we're doing, because they could see that this was a serious scientific effort, and that we had actually put together an assay which they could then take, and this is helping them de-risk. So that's one approach. And then there's another good approach with a problem with imaging is for a disease called CMT type 1B. This is caused by mutations within the peripheral myelin protein 0 gene, or P0. And again, there's over 200 different mutations that cause this. But one of the main pathways now is a problem within cells in which the mutation within the gene makes a protein that can't be folded correctly within the endoplasmic reticulum. It causes a process called the unfolded protein response. And in a series of papers over the last 5 years, and work that's been led by Larry Ravitz, it's been shown that if you can attenuate the unfolded protein response, you can develop treatment in more than one rodent model of CMT1B. So again, this is a rational way to try to develop a treatment for the disease, and you can use immunohistochemistry or firefly and nanoluciferase in similar ways to what I showed you before to develop an assay which can be used to look at candidate treatments that can attenuate the UPR. So I don't want to go too much more into like basic biology, but I think the lesson for this talk is that when you are working with patient foundations like the CMTA, it's important to help them focus on the real questions at hand, which scientific experts can do, and then they can also go out and they can fundraise, and you can bring in resources, and if you partner with sciences, you can actually develop robust assays, which then will attract interest. And then, again, so these are candidate therapies for CMT1A and CMT1B. Because the science was strong, we were able to develop partnerships with Sanofi Genzyme, which are still going on. We have another partnership that we're doing with a company called Inflectus to develop potential treatments for CMT1B. And this is because there's solid science so that the companies don't have to take the risk of trying to develop assays in disorders they don't understand. Okay? So solid science, and again, when you do clinical trials, you're spending years of your life in these trials. You are putting a lot of resources. Clinical trials are not cheap. So because the responsibility to yourselves, to the patients, and to the science, to when you get involved in trials, to the best of your ability, make sure that you're buying in intellectually to the rationale behind them. Okay, the next question is, we have these patients, we have these diseases, one of which is extremely slowly progressive, T1A, and I'm going to focus on that a little bit next. Because how are we going to tell if a treatment works? And the way to do that, as you know, is to develop outcome measures. And this is further proof that I was certainly no expert, because I'm just going to go through how things have worked for us here and some of the lessons we've learned. So when we first started trying to think about clinical trials, there was a breakthrough in CMT1A that there was an investigator in France who used molecular biology to make a mouse model of CMT1A. And the mouse got peripheral neuropathy, and the paper got published, I think it was in Nature Medicine, but a very prominent journal. And everybody was really excited because they showed pathological abnormalities, they showed changes in nerve conduction velocities. And then he did one more thing that really got everybody excited, is that in co-cultures, if you take neurons and Schwann cells and put them in culture, you can make them myelinate. And this is work from Richard and Mary Buggy over many years ago. But they only myelinate if you put in vitamin C, because vitamin C is necessary for the extracellular matrix to work, and you can get co-cultures to myelinate. And this Michel Fontes from France gave his mice vitamin C, and in this paper that I mentioned a minute ago, he showed that the mice got better. So we were totally psyched. We had a drug, we had a mouse model, we sort of thought we knew about the biology, but we didn't have any way to measure change. So none of us had any experience in this, although people like me were clinicians. So we went in the literature and we found what was called the total neuropathy score, which was a way of measuring life-dependent neuropathies. And I'm not going to go into details, but all of these are life-dependent. And we modified that to develop the CMT neuropathy score. And this is a composite score of symptoms, which are in yellow, findings on the exam, which are in green, and findings on nerve conductions, which are in blue. And we set this up so it's length dependent. And if you had the worst possible score for each item, you got 4. If it was normal, you got 0. The maximum score is 36. And we published and showed that it was reproducible. And we looked at our prospective study because we thought we asked questions in always the same way. We used a little bit of retrospective data, and we were proud that we were able to show that there was progression over a couple of years doing the scale, and we were ready for a clinical trial. And we went down to the group at NIH, and Robin was there, and that's where I first met Robin, and she was very kind to me, and we got yelled at by all the panel members, but nevertheless we plowed ahead because we were going to treat CMT1A with vitamin C, and we also figured that this was out there. Patients were starting to treat themselves, so we wanted to get an answer, and we did parallel trials, one in Europe and one in the United States, and this will be a great surprise to you, but CMT1A was not cured, and the treatment was not effective. And moreover, when we looked at our outcome measures, we found that our natural history studies were all baloney, and that the progression we had seen in the absence of a trial was no longer there. So not only did the drug not work for any of these studies, but the natural history study, all of a sudden, the rate of progression declined. So again, the lesson we learned here was, again, the outcome measure. It turned out the mouse model was not really a good model of CMT1A. It was much more severe. It was a single mouse model. And again, we learned that natural history is not the same thing as the placebo group. So we have gone forward. To give ourselves a little bit of credit, we had a couple of ENMC meetings in Naarden, the European Neuromuscular Consortia, and we tweaked the CMT neuropathy score, and then we more recently have subjected it to rash analysis, which I'm just going to show you on the right part of the slide here. You see these balls here, and this basically is showing that the CMT neuropathy score, which we were so proud of, was not linear, that it could detect patients who had mild problems, it could detect people who had severe problems, but everybody else clumped in the middle. So we subsequently have weighted the score to make it linear. And then we also had to do one other thing, which before we had talked about longitudinal data with like 50 or 70 patients. But that really isn't adequate for something that's slowly progressive. And I'm not going to go into power analysis here, but you often need hundreds of patients for these. And so we were fortunate enough to be awarded a rare disease clinical research network consortium, where we have centers all around the world, and we cross-train each other using on this outcome measure and others, and we now have over 1,000 patients with CMT1A we can look at. And so we are also, as we got into develop this consortium, and it became clear that we were serious about natural history data, getting back to advocacy groups, now this started to build up here. Because now, not only do we have buy-in from the CMTA, but the Muscular Dystrophy Association, the CMT UK, the Telethon, and CMTA Australia. Because once we start to get something of the magnitude of this international consortium going, then you get much more buy-in from the patient advocacy groups, and then this partnership can sort of go. And with this consortium and the weighted rash studies, first of all, we've been able to get new longitudinal data, and I think we're much more rigorous in how we perform these weighted scores. But now we have hundreds of patients, and we can see change within a 2-year period. And so we're starting to feel better about our ability to have a clinical scale for CMT1A. But as we learn about powering studies, the change over this 2-year period is small, so that using again, power analysis, we calculate that we'll probably need a double-blind study where there are 300 patients in each arm, which is a challenge for recruitment for something like CMT1A, and it's going to be a real challenge for some of the rare forms of CMT. So that was with an outcome measure that was a composite score. But as I have said, I'm not an expert, and we were learning as we went along, and we began realizing that our composite score, although we have a lot of data and it's useful, is not perfect for a couple of reasons. First, it doesn't look at function, it's just a static measurement. And the second thing is that we were pretty sure we knew what was mild, moderate, or severe, but we never asked any patient about that. We were the experienced doctors, and we were sure that we knew what was important. But actually, patients, whether they could feel a tuning fork or vibrate better at their knee or the ankle, they may not have thought that that was the most important thing in their life. So we expanded with the help of Josh Burns and Rick Finkel, and we developed a much more functional assay. And we also were realizing that we had to do studies in as early as possible, because there's a lot of secondary changes we want to try to avoid. So we developed the CMT-PED score, and I'm just going to go through this a little bit quickly. This is just a functional score where kids have to do things like they have to work with pegs with their hands, they have to do a 6-minute walk, they have to do balance on 1 foot, 2 feet. It's many things that they have to do in this study. And then because kids change as they grow up, we, Josh put together a calculator that's on the computer, and when you put all the data in, it gives you a normalized value for the child's sex and age. And Josh also put together what's called the 1,000 Norms project. This is in Australia, where he looked at 1,000 children in the normal population just to get good normative data for all of those scores. And then, so we're quite pleased with this because this has been validated, shown to correlate with our CMT exam score, in patients who have had both. And just in the last week, we've had this paper accepted in the Annals of Neurology, which, particularly for CMT1A, is going to shows a progression over time in CMT1A at a level where instead of needing 350 patients in an arm with a clinical outcome measure, we may be down to like 150. And this is work from David Herman, again, the value of a consortium. We have lots of experts. And David is working on taking this into adults. So we now have what's called the functional outcome measure. And we have now about 40 or 50 patients with this in adults, which is almost the same functional scale as with kids. And again, it looks like it's matching up well. So what else would we need to be able to measure change in time? We have a functional outcome measure, and I should say that the functional outcome measure also is linked to a patient-reported quality of life instrument. So how else do we tell if diseases are progressing? Well, I think, and to make things more robust, I think you have to start thinking about things like biomarkers. Okay? And so we have been looking in serum and plasma, but in the CMT world and for CMT1A, the most exciting work comes from Mary Riley's group in London, where they are looking at the free fat fraction in calf muscles of patients with CMT1A. So within muscle, if it gets denervated or if you have muscle disease, there are myocytes or else satellite cells that change their gene expression and become adipocytes, and they make fat within the muscle. So this is not fat from lying around. This is fat from muscle damage. And if you look here, here's a 19-year-old with CMT1A with only a little bit of fat, 1%. Here's a 37-year-old with 18%. And then here is a 53-year-old with about 80% fat distribution. And what Mary and also us in collaboration with her more recently have shown is that this change to fat distribution occurs in a measurable amount within a year, which really becomes a much more sensitive marker for disease progression than any of the clinical markers. So this is just showing you the longitudinal data. And the individual muscles here are color-coded. It's a little bit hard for me to see when I'm looking here, but I think in red, I think that's angiotip, and the percentage, let's come back, lost my arrow. But if you look at the angiotip at the top, which is the baseline, and then if you look at the bottom one, a year later, you'll see that the percentage increases. It increases for all of these muscles. And this is a busy slide, but if you sort of look at the red box, what that's showing you, and actually the red doesn't show up here. So each of these here are the percentages of fat fraction for muscles at baseline. And what this shows is at the end of a year, the free fat fraction increases in all of these. And if you eliminate the modest 10% and the worst 10%, that you can detect progression in such a way that with the data now, you can measure reproducible progression in about 20 or 30 patients in an arm for CMT1A. So again, we're getting biomarkers. And for CMT1A, we also want to be able to develop a way to measure whether PMP22 levels reduce with the treatment. And so we've developed, with John Severa, we've developed a skin biopsy assay. I'm just going to go through this quickly, in which if you look at patients with CMT1A versus controls, you see that the PMP22 levels are higher, but there's a lot of spread. Here's the control population. But if you normalize to a Schwartz-cell gene called glutamine, which is in the part of myelin, then you can now tighten that up so that you actually have like a clear difference in the PMP22 levels. So I sort of feel like I'm starting to get a bit long-winded here, so I'm just going to try to summarize what I tried to say in the last few slides, is that by working together with people and really doing as carefully as possible with big numbers of patients, we've been now able to put together clinical outcome measures that show change over time that we believe in. We've been able to expand those to make them be functional, have patient input in them. We also are developing biomarkers which we think can show change. We're finding a way to measure PMP22 levels in serum. And we also have got expertise with Mike McDermott and colleagues at the University of Rochester doing things that you're doing in your coursework here, which is to try to put together well-powered proposals. And with that, we now have answers to these questions, like some scientific rationale, outcome measures, trial design, and infrastructure. So the result of this is sometimes we reach out to pharmacy or industry, but now they reach out to us because not only do we have the science, but we have the natural history data. So all of these companies now are reaching out to our consortium and investigators in our group, not because I know what I'm doing, but because we have really answers to all of those questions before that I showed you on the previous slide. And it is because of that you can take investigator-driven trial studies to industry, and also that you can involve patient foundations. So again, I think this is just a repeat of what I've said. This is our group here at Iowa, and here are many of our collaborators within the Inherited Neuropathy Consortium. And thanks for letting me talk. I'm happy to take questions if you have time. Yes?
That's right. You mentioned about the quantitative MRI.
Yes.
Are you looking at prediction models at all using the baseline quantitative MRI scores and fraction?
Yes, we are. Yeah. And again, this is something that we're collaborating with Queen Square in London, and so we have our second set of patients that are coming out with this data, and we're actually trying to get funding to expand this throughout our consortium, but along the lines of what you're saying. Okay.
Other questions?
Yeah.
Do you have any practical guidance for contacting and corresponding with industry partners that help you along there?
Yeah, I think it's just lessons learned, because at the beginning of this, we would reach out to them, and in general, they weren't all that interested. And, you know, you struggle to get somebody to talk to. They may or may not talk back, and it just never seemed to go anywhere until we had assays that they didn't have to develop, and until we had natural history data. So I think, and also I'm just going to say another sort of probably stupid thing, but when I started this, I was very high and mighty about, you know, I'm an academic, so I'm not going to lower myself to work with a company that's in there for profit. And actually, as we've gotten to work with industry, they've been great scientists. They have tools that are beyond anything I could have ever imagined, but they just have a bottom line they have to adhere to. And if you can't, if they have to start from scratch, it's just not going to work. So I guess, and if you have something that's not starting from scratch, it's been my experience that they're more than willing to talk, collaborate, and work with you. And they've been great.
Other questions? All right, thank you, Dr.
Thanks.